All right, we are ready to get started. Sorry we're a little bit late. But if you're here for machine learning best practices, I hope. My name is Christopher Brown. I am a software engineer on the Earth Engine team. I work primarily with our machine learning integration. So, today we're going to talk about machine learning best practices at a really high level. This is not neural net specific. I know some of the other stuff we've been doing has been pretty TensorFlow heavy. Just out of curiosity, who here went to neural segmentation? Okay, interesting order, but that works. Who went to TensorFlow 1? Okay, so this is cool. Yeah, it's probably still going to talk about the same content, but so in short, when I say machine learning best practices, there is no real canonical list of best practices. These are my opinion of important things that I think are generally relevant to a machine learning workflow. And furthermore, either I've encountered or I have, indirectly encountered. So though it is called best practices, we're going to start by trying to build a little bit of intuition to help explain some of why these best practices are best practices. We'll talk about data quality. When I say data quality, I don't necessarily mean sort of the accuracy of your field collections, That's not my position to comment on. We're going to be talking about data quality as it pertains to a machine learning model, depending on the type of model that you're using, depending on what you're doing. Briefly, we'll talk about success metrics, so how you actually judge the performance of a model, and really just that it's to be taken with a grain of salt, any success metric. We'll talk a little bit about constraints. This could be a loss function, anything that you're minimizing, or any component of a loss function, if this is sort of the terminology with which you're familiar. And then we will talk about neural networks, but at a really high level. I'm not going to go into where to put your batch normalization or anything, just really sort of a meta discussion of neural networks and how things sort of change. Okay, so without further ado, let's talk a little bit about intuition, about machine learning at a very high level. And a lot of times when you hear someone who maybe isn't a data scientist or just wants to use machine learning, they refer to it as this black box or this magic box that they just dump some data in and then they get a result, And it just solves the rest of the problem, the part of the problem that was sort of intractable or hard to really figure out. And I want to encourage you not to think of things this way. And though things can get complex and it can be difficult to try and conceptualize what's actually happening, you can get a high-level sort of understanding of what's actually going on that can inform your decisions. So we'll start by getting a little bit formal. So I'm going to call it classical problem solving. We solve a problem, we develop a complete process. We know the tools we're going to use, and then we apply that solution, apply that process to solve our problem. This could be like this problem can be solved by looking at two thresholds, across which I'll classify things by their NDVI. That's a process, and we know how to apply that. Machine learning is when you know some of the process, you kind of know, and then you certainly know how to apply it, And you have gaps in your process. And the whole point of machine learning is to fill in these gaps. As of 2019, we don't yet have something that will, if our unknown gaps are, how do I even begin to solve this problem and I don't know how to apply it, we don't quite have anything that can handle that. But we do have things that can handle, I kind of know how this should work, but I'm missing some gaps. In our analogy here, you have a decision tree, but you don't know where those thresholds are, and you want to find them. And this is machine learning, At least as the treatment that we give it in 2019. All right, so let's get a little bit more formal. Sometimes you'll refer to this partially solved problem or this idea as a hypothesis. This is also referred to as a model. And we can start to treat it as a function, We can say it has our inputs. These are the things that we know. Our problem is just a function. It has got parameters. And then it has some output. We refer to these inputs as features. And we refer to these gaps, these things we don't know, these question marks, as the parameters of the function, And so we can now start to say, we have a hypothesis which takes some inputs and it's parameterized by something, It's the thing that we actually want to know. We want the machine to figure out what these parameters of the hypothesis are. And there are so many different ways to find what these parameters are that at a really high level, we're not going to talk about how we find those parameters just yet. We're going to talk about simply that they exist, And that we do need to find these for some hypothesis. So we're going to build some intuition, and you might think, well, this isn't very helpful, but we'll get there. Bear with me here. So, if we're treating this as a function, right, that has some number of inputs. We can imagine the inputs to this function, so the things that we're actually trying to get a result about, these are not the parameters, as points, right, in some dimensional space, where that dimensional space is the cardinality of the set of your inputs. So if I have a function that takes 3 inputs, I can think, and these are continuously valued inputs, right? I can think I have a function that maps a point in 3D space, because there's 3 inputs, to perhaps a point in 1D space, perhaps a probability, right? If it's some sort of regression, if it's a classification problem, maybe that's some integer variable, right? So let's think of this in terms of geometry. I'm mapping some point in ND space, and n can get very high, right, to some output. So if that's our analogy, right, that really all we're building is a function that's making some geometric transform to some output, then a machine learning model is simply something that is transforming, embedding, projecting, and binning the space, that high dimensional input space, into a much lower dimensional input space, right? So if I have a problem, we'll say like an image recognition problem, say it's 256 by 256 pixels, and it's a continuously valued variable, I can say I have 65,000 dimensions. I have a point in 65,000 dimensional space, and if it's just say like an image classification problem, I am going to embed that into 1D space. And that's what a machine learning model is doing. Of course, we can say, well, I have fewer dimensions, and binning, right, is a totally different thing to talk about. And I should just say, when I say binning, I'm referring to things like decision trees, k-nearest neighbors, where instead of transforming and embedding that space, you're actually, in the case of decision trees, right, I'm adding axis-aligned splits. So I'm saying, make a different judgment about points on this side of the split than the other one. This is a binning process. K-nearest neighbors is the same way. I have a point, and then I'm looking at which bins it falls to, or which bins it's close to. So, right, we can think of this in terms of geometry. And so we're going to refer to these throughout as manifolds, right? So these objects in this really high dimensional space that form our classes, right? So I should also mention that if we're talking about some, n high-dimensional, hyperdimensional manifold, that sure, we're going to embed it into some much smaller space, but that means in that original input space, we do have some n-dimensional volume that defines the actual class, right, if it's a classification problem, or a continuous sort of field if it's a regression problem. And so a really interesting diagram that kind of illustrates all of this stuff has been this kooky GIF that's been kind of playing while I've been talking here. And this is where our input is in 2 dimensions, and we have 2 manifolds, right? Or partially defined manifolds in this case. We'll say we don't actually know what the full manifold is, and that'll actually become relevant later. But we have red and blue, and really we'd like to classify this object in 2 dimensions into 1 dimension, right? We'd like to be able to add a split at a threshold somewhere in 1 dimension so we can say yes red or yes blue. And in this case, this is actually applying a series of fully connected networks, or fully connected layers in a neural network. If you don't know what that is, that's totally fine, though I think based on the hands that were raised, all of you do. And it's showing the series of transformations that the network actually learned such that we could draw a line straight through those 2 manifolds and now in 1 dimension embed them. So that's really, for an example, in neural nets, logistic regression. This is really how it will look for anything that is doing some sort of first-order gradient method, gradient following, gradient descent, all that kind of stuff. Binning, again, is a little bit different. This is the intuition. Treat it as think of it as a geometry, right? And you don't if it's n dimensions, don't think of it that way. Really just thinking of it in like 3D space. The analogy usually holds. Sometimes, right? So what we do, another important consideration is that these inputs are now kind of, in a way, degrees of, not in a way, they are, right? If we're using geometry as our analogy, then these are degrees of freedom. And though I am sure you can, and I can right now, think of a million different ways, we could engineer cases where this isn't true. In practice, it tends to be the case that there is a link, a positive link, between the number of inputs, so the number of degrees of freedom, and the number of parameters required to describe those objects. You may have heard of this before. This is referred to as the curse of dimensionality, right? As our degrees of freedom increase, it becomes harder and harder to describe or transform these manifolds that define our class, right? These are our class manifolds, or if it's a field, right, like a regression problem, to actually embed this field. And that being said, just a brief word on this diagram to sort of illustrate the curse of dimensionality here. So this is showing what happens when we start with an n ball, where n is number of dimensions, right? And we have 2 of them. So we have an n ball we call the shell, and then we have an interior ball. And this ball, in the beginning, right, if we just think of it in terms of 2 dimensions, is a shape where its radius is 5% of the radius of the shell, right? So we have one ball inside of another one, and the interior's radius is 5% of the larger ball. And we ask the question, what is the ratio of the volume, or what is the ratio of the area from the shell to the smaller ball to that inside the smaller ball, right? And so if it's only 5%, well, we should expect, you would imagine something around like 5% squared, right? Something that has to do with the area. And in fact, that's not the case. As we increase the number of dimensions of our n sphere embedded in another n sphere or n ball, that ratio tends towards 1. And in fact, the area, that 5% radial difference between these 2 n spheres, dominates the whole volume of these 2 solids, or dominates the volume of the ratio of the solids. So as your degrees of freedom increase, even in the simplest cases, it becomes increasingly difficult to try and describe these manifolds. So that being said, right, so it's sort of like doom and gloom, right? Okay, the more inputs you have, the more parameters you need, the more difficult it is. And this brings us to kind of the first best practice of machine learning that sort of will drive the rest of what we talk about, and really anybody would tell you. And it's simply Occam's razor, right? It's kind of obvious at this point. As your inputs increase, so do tend the degrees of freedom, and so do the number of parameters we expect. And so as the number of parameters increase, the interpretability of your model goes down, right? So the more ways in which we describe this model, these gaps, these things we don't know, the harder it is to actually understand what's going on, right? Because we didn't fill in these gaps ourselves. If we go back to that original tree, the more parameters we have, the less prior knowledge we had about that model. So interpretability goes down. As we increase the parameters, then, the recovery of those parameters, the cost of recovery goes up. And so, in general, solving a problem, right, and this is kind of obvious wisdom, but it's important to talk about, right? Solving a problem with a machine learning model should be done with the principle that simpler is better. More interpretable is better. And not just because it's easier, right, because it becomes more expensive. And this means that maybe neural nets aren't the first place you jump. And this also means that, well, I don't know how to solve this problem, so let me get a long list of, NDVI, and then we'll get the, mean NDVI over here and variance of the NDVI, and then I'll take all the bands from Landsat, and then the local, smoothed kernel of the infrared band. You can make up all sorts of stuff. And this is actually not an uncommon practice, and just take this giant stack of features and then put it into a model, and then if it's getting a good result, that's good enough. That's very hard to iterate on, right? And it's very hard to understand the underlying process so that you can actually improve the model, because that's sort of a dead end at that point. In cases when you're using something now like random forest or any sort of model where you can get some metric of interpretability, then maybe this isn't a bad idea as long as your end goal is to reduce the number of parameters that describe this model. So, right, that's sort of the fundamental principle that will guide some of the things we'll talk about here, and hopefully some intuition to help you understand why some of these things matter. So before I go on, any questions? Okay. So we're going to jump into talking a little bit about data that goes into the model, and then sort of how it changes when you're using a different model, and what you have to think about, right? Because we're not treating these as black boxes anymore. We're treating them as these either binning or transforming functions of an input geometry that's in some high dimensional space. So you can't start to talk about, right, data quality without talking about bias. And it's complicated, right? So it's probably fairly obvious that when we have some data that we want to train a model with, we're familiar with the term overtraining, right? So we want to balance our classes. We want to understand things equitably. So we're going to collect, great, I've got 3 classes. I'll collect 33% of each class, and I'm good. I'm ready to go. Not quite, right? So obviously, you want your model to predict data without overfitting to one class. But the problem is, it's not quite so easy. Because if we go back to this analogy about manifolds in some high dimensional space, right? It's entirely possible that sure, we've collected an equitable number of points in these high dimensional volumes within these manifolds. However, where the points lie in the manifolds are not actually distributed in any one manifold. And that's kind of hard to explain, but you can imagine, and I said yesterday I should have had a diagram for this. But if you have some shape, right, and it just has perhaps like a long peak somewhere on this shape, and if all of your points are collected within that peak, then you're not fully describing that manifold very well. And This sort of intuitive explanation leads to something called covariate shift between your training data, or even your validation data, and then what happens in production, right? Because you aren't actually capturing that, because really your goal is to try and sample an even number of points such as you're describing this high dimensional shape. So even if you've balanced your classes when you're collecting data, you still might not have actually balanced the samples within any one class. And that's a little bit harder to do. And it's especially hard because we don't know what that manifold is, right? The whole point of machine learning is to try and find out what that manifold is, or really just not care about it, or embed it down to something that we can just slice, or add a threshold to, or whatever. So this is another important thing. And right, so as it says, diversity of examples within a class is just as important as diversity of members within of actual classes. And an example up here, something we actually ran into. So Rebecca talked about Project Earth in the keynote. And one of the things we did is, we did our due diligence. We tried to collect, of the points that we had, we were trying to filter this to an equitable number of points per class. And the training data set that we have, this was actually a model that was trained on points. If you were in the neural segmentation class, we talked a little bit about how we did a segmentation model with points. Excuse me. And we were feeling pretty good. Like, okay, this is nice. These seem to have a nice balance between biome and region, and this is kind of what we expect for a good training data set. However, when we looked at some of the results, we had this was a land cover classifier. It had a bare ground class. And suddenly, all of the rivers and lakes in the world had a beach, which they didn't have before. And it was because when we had been collecting our points to define our class of water, there were just about the same number of points per class, right? But we didn't collect enough points close to the shoreline. So we didn't actually get full coverage of that manifold when we were collecting our data. And so now you'll see, this is, again, a map of bare ground, and it's correctly getting the bare ground that's at the edge of a landmass, but then it's predicting bare ground where it really isn't, because we didn't actually sample classes here, or sample points here. So intra-class bias is just as relevant as total class bias, right? So, okay, we've talked a little bit about that. Something that isn't so important if you're using binning methods, so if you're using k-nearest neighbors or some flavor, if you're using some sort of tree-based classifier, this might not be so relevant, but normalization is really an important pre-processing step if you have data that's, again, going to be fed into some model that's minimizing based off of these gradient methods, right? And really, this is because when you remember, you have to compute the gradient for each, you compute the gradient, that's across all the parameters of your model, you take a step, and if you have a range that is much larger, some input range is much larger than another input range, the gradient's going to dominate in that direction. And since your learning rate is usually fixed per parameter, you can use adaptive learning rates to help this a little bit. But again, that's not something we're getting into. Your gradient descent is less numerically stable and will take longer, and usually will converge to a much further minima than the one that you'd really like, right, than the actual minima. So, right, and I'm talking about normalizing data. I should really say, what does it mean to normalize your data? And that's really just to transform it to a regular range, right? So for those of you who are familiar with z-scoring, this is a pretty common way to deal with data that's sort of sampled from naturally occurring processes, right? So one common thing is, okay, I've got some, we'll say sentinel bands, and I want to sample some points from these sentinel bands. Okay, I've got the, say, mean and variance of band 2 in Sentinel. And I'm going to use these to normalize my data so that all the ranges are the same and that no one direction dominates the gradient following method. One word of caution. So this is a pretty specific word of caution, but if you do the thing that I just described with satellite imagery, remember, lots of things saturate at the high end the sensor. So there will be a bias towards the upper end of the readings on that sensor. So taking the mean isn't always really what you want. You can try the median, that's a little less biased, but it's still biased upwards. So it does require a little bit of careful consideration in this case. This might be the kind of thing where you just throw out outliers that are saturating the sensor or keep some percentage of them. But right, normalization really is a technique that improves the performance of methods that are following the gradient or are computing derivatives for each of these parameters. Okay, so we're talking about inputs, ways that we pre-process, ways that we improve the performance of our model just with data quality, right? And again, for some of you, this might be super obvious, but it's worth talking about. And this is categorical versus ordinal features, right? Ordinal features are easy. I put the descriptions in the wrong order, but we'll start with categorical because it's on the slide. Those are features which you cannot put in any order, right? So if I have bananas, cats, walnuts, these are classes, unless you have some definitive ordering, I don't know, dislike that you'd like to put them in, it doesn't really make any sense. So these are, right, you can't really put them in an order. And then ordinal features become something like a continuous variable, right? Like, so this would be the actual sampled value from some Landsat band or something like that. Okay, so that's obvious, right? What maybe is obvious and maybe isn't obvious is something that's pretty common, right? So because we are treating these hypotheses as functions, right, we tend to think, okay, we need to express everything as some numeric value. So, okay, I've got some category which really is just a sort of class ID. Maybe I'll make that a single input, and I'll squash it into one variable. So in this case, in our example, 0 is banana, 1/2 is a cat, and 1 is onion, right? So that's what we'll that'll be an input feature, and we'll just call that class. We'll see why in a second this isn't a great idea, but, why sort of in terms of the actual, our intuitive understanding of how a machine learning model actually works, this doesn't make any sense. But even under analysis, this doesn't really make any sense, right? So if my classifier is just trying to find out what let's say the, mineral, animal, vegetable, right? And the output is vegetable, and we're including bananas in this class. What's the expected value if we have even classes in this case? It's cat, right? And that doesn't really make any sense. So it's hard to analyze and really make sense of the output of your model unless you then go ahead and break up the classes afterwards. So that's really not a good idea, and we'll get into more of why that's not a good idea in a second. But we do want to talk about categorical features, because then what do, right? How do we represent categorical data that can't be ordered as inputs to the model? Often this is done using something called one-hot encoding. So if I have 3 different categories, I have 3 new inputs, right? It's not one input. And we treat these as probabilities, right? So the probability that this object, this input point, is a cat is 1 in this case, or class C is 1. And this makes sense, right? Because now we have these sort of continuous outputs as we'd expect from a function. Smoothness is nice. There is an obvious problem here. So what if we're talking about like words in the English language? What if we're talking about a huge number of things that can't be put in order? Do we add, okay, so let's go back to the, words in English, right? If we wanted to make a one-hot encoding as an input to our model, that's going to get really, really big. That's going to get huge. Even if we use just the words that are confined to some book, it's going to be a little bit overwhelming. So what we can do is build something called an embedding. So instead of building a categorical feature, which is good for a simple and small number of a one-hot encoding, which is good for a small number of simple categorical features, we build an embedding, which represents every item in that set as a point in some ND space. This diagram is showing, okay, we've got some key phrases from a book, and we've built an embedding. And ideally, we want these embeddings to have this property that semantically similar embeddings are close to each other in embedding space. So animals, horse, dog, cat should all be close to each other. Building an embedding is a whole other discussion. A lot of research has been done. Oftentimes, you can get an embedding that just does what you want. So for an example, we're talking about English words in this case. You can find find projects where people have actually embedded dictionaries of words or other categorical objects using usually some sort of machine learning algorithm. So again, this is how you deal with sets of very high cardinality. Doesn't make sense to make a one-hot vector. Oh, and another thing I want to point out here. So because most of you have done the neural net stuff already, and you're probably already thinking in terms of neural nets, just a plug for something called label smoothing. So oftentimes when we're representing things as categorical features, we do this one-hot, right? One-hot encoding. So we say, hey, 1, the probability is maximal probability. This is what the input object is. So when we're actually building labels, when we want something to predict categorical features, oftentimes we'll do something like softmax, right? If you're not familiar with what softmax is, it's sort of a normalizing procedure that takes some vectored output and normalize it such that this discrete distribution sums to 1 after being sigmoid activated, which is this sort of saturation function. So anything that passes through a saturation function, right, when you're building a neural net, remember that to get that activation to equal 1, the output of that activation function equal to 1, technically it never, well, unless it's the limit as you approach infinity in the positive direction, right? So that doesn't really make sense to ask the model to do that. So really you're asking the model to just output the highest value it possibly can, as long as it can, to try and label a value that's a categorical feature using some saturating function as 1. So if you're using something like softmax neural net, folks, or hyperbolic tangent, any of these things to sort of shape the outputs of your model, instead of labeling with 1, label with something like 0.9, or label with something like 0.1 if it's a class you don't want to predict. Simply by doing this, we're no longer asking the model to predict the highest value it can, or output the highest logit it can. Again, and I'm assuming this is a neural net crowd. So yeah, employ label smoothing. If my explanation here wasn't very good, definitely look it up. Basically, it's a good way to prevent overtraining because you're no longer trying to activate very high on all of these 1 inputs that is just sort of infeasible for the model to do in the first place. All right, so I've made my plug for label smoothing. Okay, so discontinuity in your input data is also somewhat relevant, right? So we've been making this geometric analogy. And even when we were talking about embeddings, we were saying that points in embedding space that are semantically similar should be close together, right? So we're sort of coming to the smoothness property that we'd prefer for our inputs, right? As an input slowly changes, we also expect the output to slowly change, right? As we start to add, as there start to be hard changes, spikes, or even complete discontinuities, things that we couldn't differentiate in the input space to our model, that becomes a lot more difficult to transform, right? Because we're expecting that once some input crosses a boundary, the output of our model should drastically change. So one such technique that violates this smoothness is that categorical feature squashing into an ordinal input, right? So that doesn't really work. Another somewhat common practice is to use some component of seasonality, right? So I want to train my model, and I'd like my model to perform differently depending on whether this was in spring, summer, fall, winter, that kind of thing. There's a couple ways you could do this. You could even have a categorical feature, right? That is the season. That's the input to your model. Fairly common is to just have a single variable where 0 is the start of the year and 1 is the end of the year. You run into this problem now that points in winter, just in this example, I don't know how you're actually splitting it, have this sort of discontinuous separation where now at both ends along this seasonality axis, you want things to be similar. So if we think about this semantically, that's a discontinuity, right? Because we really like to take the ends of this manifold and connect them. Because no longer, right, are points actually close to each other in embedding space if they're semantically similar. We're violating that smoothness principle. So this is also not a great idea. Usually what we do here, if you have some cyclic feature, is to, instead of treating it as a polar coordinate, is to actually project that into like the sine and cosine of your angle, right, of your seasonality. So now this way, we're actually maintaining the smoothness in the input space. Okay, so we've talked a little bit about data. So we worked on kind of trying to define this in terms of with an intuitive description. We talked about data quality, data as it's the input to a model. Now we're going to talk about, very briefly, success metrics. And water and forests are free, and that'll become relevant in a second. Actually, I'm sorry, before I just soldier on here, does anybody have any questions? You first.
One thing you said something about scaling with the z-score, but there's also like this min-max scaling. How does it differ and when to use?
Sure. So in both of these cases, right, what we're doing is we're redefining the range of so we're doing two things, right? We are moving the mean of our data category, and then we are changing the range. And it depends on what's appropriate, right? So for an example, if I do a mean, and so if I do something like a z-score, right? I'm not actually guaranteeing a range, right? At this point, I'm saying, I'd like the standard deviation to be within 1, but I'm not saying, right, just how far the extent of these points will be. So if I do that, usually what it makes sense to do is if you're using something like a z-score is to then use one of these saturating functions. So such that you have a true defined range of your input data. If you're using something like a min-max, then you are actually defining that range. And that might not be something you need to do anymore. However, if you are using a min-max, you want to make sure that at least your data is, at the mean of that min-max, right, the halfway point, that your data is at least following either something like a normal distribution, if you're doing things like batch normalization and all that other good stuff, or that there aren't crazy outliers, right? So you would do something like give me the 90th percentile, if you wanted to do a min-max range and then throw out outliers. Or use a saturating function. And I realized I didn't even repeat your question, and I said I was going to repeat questions. By the way, that question was, right, I want to perform some sort of normalization to my input data, as we discussed. What's the difference between taking the min-max and using that to squash my range and doing something like a z-score? And you had a question over here.
Oh, yeah. To wrap my head around it, what's an example of embedding for remote sensing applications? Would it be grouping like similar land cover classes?
Yes, so an example of, right, so one thing we could think of is if you have a large number of land cover classes, in fact, the only thing that I've talked to somebody directly about this week, but the first thing that comes to mind are like species. So if we have a category that is type of tree or something, or even type of animal, and it's hard to describe this, and there are similarities, but we're not describing this in terms of like, okay, it's got a trunk that's this long, right? We're not actually breaking down into some component-wise description of the object. And I also didn't say your question back for the recording. Sorry, recording. One sec, hold that thought. The question was, what's an example of a categorical embedding for remote sensing? And we're saying one example might be species, right? Things that are difficult to describe as a component-wise vector of feature descriptors, right? That would be difficult to do. Another option is to instead embed this very sort of large taxonomy or species taxonomy into 3D space or something like that. It's helpful. Okay, so we will now move to now rewinding the clock. We're going to now talk about success metrics. And this is somewhat opinion and probably pretty obvious, but again, it's something I think we need to talk about. So we're back to bias, right? Bias doesn't just screw up models that have a tendency to overfit, like neural networks, but it also has a tendency to screw up your success metrics, right? So the obvious example is I have a category which is 90% trees, or excuse me, I have a data set which is 90% trees, and I'm predicting something like land cover, because that's our straw man for the day. And my metric is global accuracy. Okay. If I'm scoring 90%, what does that actually tell me about the performance of the model, right? At that point, I could have just always said tree and been right? This is the whole stopped clock is correct twice a day analogy. So, okay, all right. But we were smarter than that. We collected an even number of class points, so we're not going to run into this problem when we're computing a global accuracy to publish how great our model is. The problem is that things like tree, and again, this is just this analogy, you can extend this to whatever your problem domain is, but certain categories of objects are free, like water and forest in this case, if you're doing land cover mapping. And so if your success metric for your model is simply the mean class accuracy per class, you're always going to get this free improvement, because water is something you could basically predict fairly well with something like NDWI that the model will learn very easily. Or trees, which the model will learn very easily, and the things you really care about that are really hard to predict, like agriculture or wetlands, right? Something in this, if we're talking about the sort of multimodal output, these are really difficult. And if these scores are low, you need to take them into consideration, right? So it's to be done with a grain of salt, right? And yeah, so even if you're reporting a single metric, what is that single metric you're reporting? Do you report the minimum class accuracy? It's really hard to say, and it really depends on your problem domain. Really where I'm getting at here, though, is to think not just about, yay, I got to get my number as high as possible, but really what's the meaning of that number? And it's going to help you develop a model, too, if you know what you're actually optimizing for. So just also just sort of a maybe kind of obvious thing here. training accuracy is kind of useless, especially in neural network world. So publishing that, hey, we did this well on my, my training data set, I killed it. Yeah, that's not really useful, right? Because of this whole covariate shift problem that happens in the real world. You might say, okay, well, don't worry, we're doing a little bit of holdout here. I've got my validation set, and that's on which I'm going to report accuracy or something like that, my mean class accuracy. And okay, usually that's fine, but it's still, these types of numbers are to be taken with a grain of salt, right? Because even when you're developing your model, you are hill climbing on that accuracy, usually, right? Especially if you're doing some sort of automated hyperparameter tuning, the machine is hill climbing on your validation set. When you're cross-validating, it's a form of learning in that case. And so you can easily run into this problem of covariate shift if you have parts of this manifold that are now no longer being predicted well because you're just predicting your samples really well. And okay, then we can say, well, that's why we have a test set. And then hopefully your test set is you're not hill climbing on your test set, and it's very hard to be completely independent when you're reporting metrics on a model. You could continue this argument in a chain forever, that you're always hill climbing on something. So really, keep in mind that the best metric of how well a model's doing is how well does it actually perform in practice, right? Does it actually solve the problem? Regardless of what your per class prediction is, what's really important is that either somebody's looking at it and able to use it to take action, or it's actually leading to some impactful change, right? Unfortunately, the numbers are only so good when it comes to performance of a machine learning model. And again, this has a lot to do with the fact that we don't know what these input manifolds look like, right? If we just knew what those looked like, we could easily say, yes, this number is an appropriate representation of the actual data in its original n-dimensional space. Okay. Yeah, so I guess, right, maybe we could talk a little bit just about sort of some success metrics, some actual success metrics. So what's that?
Repeat the question.
Thank you. Yeah, you're gonna have to do that every time I answer a question because I'm just not gonna remember. Right, so is it possible to output multiple metrics, in this case, per pixel accuracy and class accuracy? How will we do it across classes? So sure, right? We can combine whatever set of metrics that we want. It is worth discussing, right, maybe some metrics that are appropriate for certain problems. So if you're simply doing like a tile level classification, if there's no sort of pixels involved, per class accuracy totally makes sense. That's really the only reasonable metric that you can use. Reasonable metric that you can use, some per class metrics only really reasonable. Now, if you have things like single pixels, sure, you could do still something like a per class accuracy, but something like mean intersection over union might be a little more appropriate in this case. Because that's a more intuitive way of describing what's actually happening here. Sure, this class was mispredicted, but how much does this intersection actually, what's the ratio of the intersection to the union? Yeah, that might be relevant. Of course, there's a whole field describing binary classification accuracies like F1, or metrics like F1 score and recall and precision. Yeah, I mean, it's really domain independent. Domain dependent. But yeah, we can, right tool for the job. If you want to talk about how to, different things that we can do, I do have office hours later. Okay, so the next piece I want to talk about are constraints, or loss functions. I'm going to call them because I've called them constraints yesterday, and I think that was misleading. So these are, right, not every model we can apply arbitrary constraints to, right? So something like a strict linear regression, there's some flexibility there. Binning, not so much. It's hard if you have just a cart classifier or a random forest in the classical sense to really impose some arbitrary constraint. Things like gradient boosting and neural networks, however, because these are gradient following algorithms, we can actually impose some fairly flexible constraints, and for good reason. So we're working on a machine learning problem. What are some useful things to think about and do when we're constraining the function that we're minimizing, right? The loss of our hypothesis against the parameters. So a pretty common thing to do, but not everybody does it, is just to weight excuse me, I should say why we would even do this, right? If you're trying to fight bias in your input data, Or if you're trying to improve performance on a specific use case or a specific characteristic of your prediction to your ground truths, weighting individual predictions is usually pretty free, right? Sometimes it's something we can do in an automatable way. If, for an example, we have a data set and it's something like Big EarthNet, whoever's familiar, and like our burned area count is 310 labels versus forests, which is in the tens of thousands, right? We don't really want to cut that down so that those 3 orders of magnitude, we now have just 100 labels per class. That's not really useful. So what we instead could do is we could weight these labels such that our model, the gradient, is larger when we mispredict or when we deviate from a prediction for a class that's less present. This is a bias fighting technique. This won't necessarily improve your overall accuracy, but it totally can. And not in every case, but often it does. Experimentally, internally, this is something that's actually improved our overall accuracy, not just the accuracy for mispredicted or underperforming classes. Our total MIOU went up by just weighting some labels more heavily than others, especially when you're using neural nets, because it doesn't take a lot of entropic capacity, as we described, to understand water, right, based on some inputs. But understanding something like wetlands is a lot harder. So by increasing the gradient in the direction of labels that are harder to predict, weighting is a really easy way to do it. In a really famous example of weighting is, just because it's something a lot of you are familiar with, is UNets, right? So those of you who are in the neural segmentation class or have ever explored semantic segmentation models might be familiar with a UNet, and what they did is they really wanted to predict well a binary mask at the edges of a biological something. I don't actually know what they were predicting. But I do know that the edges, right, the segmentation, they wanted to predict the edges really well because it was quite easy to predict the interiors of these, we'll say, cells. I unfortunately don't remember what the paper was concerning. And so they weighted the loss at the edges of these objects they were trying to find and increased performance where it really mattered because it was already easy for the model to predict the interior. So yeah, weighting on a label basis, a per pixel basis, is almost a free way to improve performance if you have a loss function that you can sort of control yourself. One of the greatest sort of developments and ways to improve performance for free is multitasking with a model. Again, it's a little clearer how to build a model that's multitasking when we get into neural net and, again, gradient boosting world. But multitasking is training a model where some part of that model is shared. Or excuse me, is training a model to do multiple things where in each of those things, some part of the model is shared. Really, there's sort of two of the largest benefits you get from multitasking. The first one's kind of obvious, right? If I have a training data set if I have a big label data set, because that's easy to collect, well, comparatively easy to collect, right? And I have a per pixel, much smaller labeling data set, which was much more expensive and laborious to collect, I probably have a lot more of the first one, right? I probably have we'll go back to the Big EarthNet example, 500,000 tile labels and maybe just 1,000 labeled dense patches. If these were annotated from, say, Sentinel or the same underlying imagery, what I could do is train, we'll go back to the neural net case, train something called a backbone or train some piece of a neural net to understand how to build sort of a semantic description of the inputs, and then I have one thing that builds the segmentation output and one thing that labels the images. These are referred to as heads. And this diagram does a good job of kind of explaining how multitask learning works. In a specific case, another grain of salt here, this is a huge field, right? A lot of work has been done in multitask learning. I could not even begin to scratch the surface. But some very simple multitask learning is a good way to effectively increase the size of your inputs, the amount of data that you have to train a model. And then there's a really sort of other nice benefit that you get this inductive bias towards solutions that your model is learning that generalize better, right? Because now you're working across multiple tasks. And so you now need to find a sort of feature hierarchy descriptor, if we're talking in terms of convolutional neural nets, that applies to all of your tasks. And so now, when we were talking about covariate shift, this becomes less likely when we're finding solutions that are more generalizable. So yeah, I don't want to say too much because I'm not an expert on multitask learning, but it's definitely worth a read. It's something we've been doing with our models to really throw more data at them, right? It's cheaper because you don't have to collect as much data, especially in the use case I mentioned when we're doing like a labeling task and we're doing a segmenting task. Yeah, so multitask learning, awesome. Another really common thing in machine learning for gradient following methods is regularization. Historically, this was referred to as shrinkage. Sort of in trying to briefly describe it, we want to bring the value of our parameters. If it's a neural net, it's a weight matrix. It could be the splits, it could be all sorts of other things. We want to reduce the value of those parameters, bring them as close to 0 as possible. In fact, we compute the L1 or the L2 distance from 0 of our parameter vector, and we want to make that as small as possible. Hence the name shrinkage. Regularization, right, we're calling it regularization now that we understand a little bit better what it's actually doing. So if you've been around the space for a while, you probably remember lasso, in which you don't just regularize, but then you remove parameters from some model, some hypothesis that are close enough to 0 that they probably don't matter. Right, there are all sorts of regularization techniques, really depending on the type of architecture or model or technique that you're using. In neural nets, if we want to think intuitively about regularization does, right, if we're reducing the values in this weight matrix, or we're reducing the Euclidean distance or the L1 distance from 0, we are effectively reducing the output of any one neuron, right? We're evening out the outputs of neurons in any one layer, or all the layers across our network. And this has the effect of smoothing out any transformations our model are actually making. Yay, smoothness, right? Input data and internally, right, in the internal tensors of the model, right? So if we're smoothing it out, we are less likely to overfit, and that's really what's key. This diagram kind of explains that concept. If we have outliers, we're not overfitting to the outliers. Sometimes this will be described in terms of a polynomial regression where we have too many parameters and we're really just overfitting the data and you have all these wild swings. It's a technique to really with the goal of reducing overfitting by smoothing out the actual transformations we're making in the middle of our network by, again, shrinking or regularizing the weight matrices if it's a neural net. So, okay. Another thing that we can do that's really easy and is especially relevant in remote sensing is this idea of using a don't care. So let's say I'm predicting something from, we'll say in this case we have an image of Landsat data, and I have a QA band, and I can say okay, this is covered with clouds. We're going back to our land cover analogy here. This area is covered with clouds. This is not. I have a nice QA mask that has this sort of well-studied correctness. And anyway, I said all that, but I don't care. I'm just going to predict the land cover for every pixel anyway, because that's an easy way to formulate a neural network, right? Easy way to formulate a model. This can lead to some problems, right? Because you're now asking the model to predict values where you couldn't actually tell, like even as a human, the best annotator in the world can't see through a cloud, right, in this example. Obviously, there's things like SAR data, but I mean, in our case here, we're just discussing in terms of like reflectance data. So we have outputs from the model that are nonsensical, right? Or perhaps we're sampling our data and we're using some automated sampling procedure to get a lot of data, and now we're sampling patches that are at the edge of a scene, or something like this if we're doing this in Earth Engine. And so we have all of this data that's masked, right? That is just like the data under the clouds. It doesn't make any sense to try and predict values here. And what you can actually do now is use this to your advantage, right? Don't ask the model to predict places where it doesn't make sense, or don't ask the model to learn how to predict areas that don't make sense to predict. So what we'll do is when we're building something like a training data set, we also collect this mask, right? That is 1 for this prediction is reasonable, is valid, and 0 for something like this prediction is completely nonsensical. Then when we do our cross entropy, then when we do the mean squared error per pixel, again, this is sort of like a pixel-wise technique, but it applies to really anything for which there's this idea of not caring. We can then multiply this mask against the per pixel loss before we take something like the mean across all pixels, right, depending on a regression task, or even mean, right, if it's something like cross entropy, or we're summing across examples. So we can help our model, we can remove noise from the training process this way, but we can also now under-collect annotations, which might be useful. So what I mean is if you have some army of annotators, right, or if you're yourself annotating images, and there's a region which you truly cannot decipher, right? Now, obviously, another grain of salt here, make sure this doesn't lead to rejection of a very specific class of annotations, but if there are these regions that are unannotatable for whatever reason, you can leave those out and then include a don't care mask so that your loss is not computed against these values, which you just didn't know. You're not trying to predict some background class. You're not trying to throw away samples that are at the edges of tiles. You can just mask it, and the model will learn what you want, and you can do this in a very automatable way.
Do these masks have to be mutually exclusive? So, for example, if there's cloud and there's Cirrus Cloud is also cloud. So, do they have to be mutually exclusive?
So, right, the question was, do we have to make a mutually exclusive mask? We can have multiple types of things. I'm assuming you're thinking we could have more than one mask, depending on what we could identify. Everything, go for it. The choice is yours, especially if you can build this loss function however you like, right? In the case of especially neural networks, it's truly, if we can differentiate this function, you can do it, right? I mean, as long as it makes sense, otherwise it's not gonna work. Sort of like, yeah, can I go to the bathroom? Yes, right? You know, like, whether or not you should do it is up to you. Sure, but you can combine this in any way that you like. Oh, and something I did forget to mention here was if we're using multitasking, right, multitask learning, we can use don't care masking to, in a really cool way, compute a gradient across multiple tasks at the same time. Because now we can don't care out the outputs that we don't care about, right? So then when we compute this loss, none of those parameters are with respect to the things we don't know. And so it's a very general technique. But yeah, so use don't cares when you don't care. So now we'll briefly talk about the really neural net specific case. I guess that's not true, but really, so non-convex problems, right, which are most. Look out for moats, and when I say moat, I'm referring to a steep local minimum, right, not the global minimum, not that which you seek. And this really punishes gradient following algorithms because it can be the case, and you can even imagine that the topology of your loss function with respect to your inputs forms a well around the true minimum. And this is not, in fact, uncommon. This is fairly common. And so what'll happen is you arrive at a minimum for which, regardless of how noisy your stochastic gradient descent is, can't actually escape. And so this is where you live. And sometimes we don't even know this is happening, and it's fine, right? Because the minimum is close enough in this diagram, for an example. But in general, it's hard to diagnose, right? To know this is really happening is difficult. And the only way you really know it's happening is if you've truly ruled everything out and your model has done something like mean collapse. Like it's just always outputting the same thing, even though nonsensically that wouldn't, it should, simply the loss function should, why, we can go lower. I can show you, model, how to do a better job. But it's not learning that because it has hit one of these modes. It's hit a steep local minimum. And this is really something to look out for. It's something very difficult to control. I can give you a concrete example of this. So recently, I was toying around with the idea of trying to predict, so not so much predict, but parse really bad date time strings. So it's been announced at this point, I think CSV ingestion is now in the code editor. CSV's ingestion is in the code editor. It was in the CLI tool for a while. Now it's in the code editor, and I think this has been announced, but Sheets integration is coming too. And in both of these cases, you can specify datetime strings, right? And currently, we just sort of say, hey, tell us the format of that datetime string. But we were thinking, man, wouldn't it be nice if we could just figure out what it is? But it's not so obvious because locales have different separators. They have different formats. Some people put days before months, months before days. Sometimes people understandably spell things wrong. Sometimes there's a UTM zone. Sometimes the UTM zone is specified in 28 different ways. Sometimes the order is switched. And it starts to become a real pain in the butt. So just toying around with, all right, how easy would it be to use a neural segmentation algorithm to parse datetime strings? Surprisingly easy. But in the development process, one of the constraints we were using was simply repredict the date, and it was using a one-hot, 0 through 9, right, categorical, trying to describe the digit once it's found it, interpretation. And the model got stuck in this really silly local minima where it was just copying the first elements on the left into the output. And no matter how hard I trained it, how many times I tried changing the batch size, this didn't change at all. Because this was a reasonable local minima. It worked pretty well, just copy the digits in. And nothing was broken about the model. This loss function was simply unsuitable for the problem I was trying to solve. And this is a very hard thing to diagnose from the get-go because, again, we don't know what the manifold looks like, and we don't know what the function, that high dimensional function against the loss actually will be. So switching it to a simpler loss function, in this case, magically everything started to work. And so, no, you're not wrong. Sometimes your loss function simply has a local minima. That's a moat that's causing it to fail. And again, this is something that's very hard to diagnose. Okay, I'm saying it's time. And I'm going to remember to repeat them. But does anybody have any questions before we go to the next part?
So you had this don't care if you don't care, but if you have like, let's say, multiple dates of a Landsat image and you want to classify the land cover, and one date has some clouds in it, and so you want to get rid of it, you can do like a fill value or like a mean or average, I don't know. And this is something different. Do you have any suggestions on how to cope with missing values that you do care about?
So you want to predict them.
Yeah, I mean, you do want the land cover.
So right, this is a different problem, right? This is where, like, instead of, we'll have enough data eventually so we cannot care about it. What if we are trying to uncover this value? Well, as you specifically might know, oh, right, I didn't repeat the question. Question is, okay, so it's not so much that we don't, what if we have a case where it's not that we don't care about the values, we really do want to try and fill in the values, and that's actually our problem, right, is that we want to predict these intermediate or these missing values. And well, there is a whole body of work going into trying to write, in terms of even generative models and content-aware filling, right? That's been co-opted by Photoshop, right? But yeah, we can talk about that because that's a whole different world. If you're actually trying to fill in missing values or something like actually predict some intermediate step.
But I don't mean in this case that you want to fill in the missing values, but let's say if you have 5 dates, but in one date there is like partial cloud cover, and you do want the whole.
Oh, but you still want a prediction using an input that you don't know.
Yes.
Okay, so right. So the question actually, the adjustment was that I didn't totally get was, okay, we have an input. In part of our input, we actually don't have a value. This doesn't make our prediction invalid, but we just don't know what this value is on the input, right? We have some stack, perhaps a time series of inputs, and we don't have the value for one of those. So to answer that question, I will kind of do it in a roundabout way. But how many of you are familiar with dropout? It's a neural network specific thing. Some of you? Okay. So dropout, this is a regularization technique, kind of like really along the same lines of the regularization techniques we were describing. And the original formulation for dropout, so I should say a little bit more about dropout. Dropout is to simply zero certain weights in your model at some step, right? So if we're thinking in terms of layers, we could zero out that weight matrix that takes us to the next layer of our model randomly as we're training. This is only something that happens during training. So the original formulation of dropout was to actually zero out inputs, right? Because the original hypothesis was that a model with enough parameters should be able to learn that this is simply noise in the data and fill in itself where these values matter, where these values don't. So that being said, this is some interesting implicit form of regularization, which doesn't even sound like a bad thing. And so I can think of 2 scenarios here. So if you have very few data elements that have this zeroing out characteristic, then your performance might be pretty poor just because this input is poorly represented in our, using our geometry analogy here. So what you could even do is now apply, so first of all, when these are inputs, treat these as 0, pick some reasonable mask value, and then use dropout, in this case, on the inputs. This kind of screws you up if you also want to do some sort of batch normalization thing, because now the distributions will change from training to testing. But dropping out on the input now is you're imposing this same constraint that will show up in your real data, on all of your data. And you're now forcing the model, hey, make sure you can learn this even when we don't have all the values present. We can talk about that more later, though. How to do that with things where the distribution changes from training to test. Okay, so we will now jump into really specifically stuff about neural networks, not even just stuff that uses gradient descent. We'll talk about neural networks in general. And as I said, we're going to talk about these at a really high level. Some of this section I will also clarify. You'll notice, unlike many of the other slides, there aren't always references at the bottom because some of this is opinion from personal experience at working at Google and just understanding the scope of what people are doing with different machine learning algorithms. So that's my disclaimer. Okay, so wow, all right, we keep name dropping neural networks, but why are they so cool? It's because they can do so many things that were intractable before, right? The real big change is that now we can solve problems that have, as we discussed, an input dimensionality of like 65,000, right? 256 by 256 tiles. And this is really the real power, right? Is that suddenly the curse of dimensionality is somehow we can fight that a little bit. We can fight the curse. I like that. That being said, also going back to Occam's razor here, they really should be a last resort, right? The parameter count in complex neural nets, and of course this doesn't apply to really simple neural networks, right? Sometimes you have a simple network. I mean, this is totally appropriate for a task for some reason. If you're in TensorFlow 1, like if you're trying to output a distribution or something that's really ill-suited to something like a binning algorithm, then this is fine. But the high parameter count makes interpreting what's actually happening in a neural net incredibly difficult. And even more so, incredibly difficult to iterate on and improve and find out why a model's doing a certain thing and why it's not doing a certain thing. Now, this current grain of salt will be that in terms of image understanding, we have made huge strides in understanding what these models, these neural networks are actually doing. A shout out to Chris Olah, his actual warping spiral GIF that I had earlier in the presentation. He's part of Google Brain and has been doing a lot of work and trying to make image understanding algorithms interpretable. So at least sometimes, in some cases, we can understand what's going on and why certain decisions are being made. But it's very hard to come up with proxies for things, or at least to my understanding, like variable importance and sort of these other usual statistical metrics that we can make because the underlying models are simple or simpler. That being said, right, now that I've said don't use neural networks, I mean do, there is a benefit, right? You can solve things that you couldn't even begin to think about, right, trying to solve. Things that are so hilariously under-constrained, right? Problems where all you know is that this image has some of class A in it, and you have some things that look like class B, and it just works, right? There is no, you didn't have to do any hard science to figure out how to actually identify these things. And a really sort of interesting application of neural networks is their ability to proxy more expensive algorithms. So if you've developed on your HPC at your university or your organization or whatever, some crazy iterative pixel technique that's looping through years of time series of data and doing all sorts of other crazy stuff that's really expensive to run, we can use neural networks as a proxy. In fact, the blog posts, we put out a blog post Monday morning talking about using neural networks as a proxy for an LCD. Right? And so the incredible expert knowledge that has been codified either in training data or these semi-automated maps or semi-automated data sets, we can capture in a neural net and then apply that neural net because, again, the ability for it to encode, actually, I guess I didn't say this, but the ability for it to encode relevant information is in the highly compressed form, not the ability. The actual compression is, right, of the data is very high. So we can use neural networks as a proxy. I will also say this because I have a weird bone to pick with this term. So every time you hear deep learning, I know they said this in TensorFlow 1, so maybe this is a repeat and this isn't interesting anymore, but it's just referring to neural networks with more than one layer. So that technically is a deep neural network. And that's just something I look out for when I'm browsing the web and I'm reading stuff about neural networks. You know, I'll see we use deep learning to solve this problem, and I'm like, yo, that's awesome, deep learning. And then their image is, it's like that, right? Like there's the deep learning model. So just there's another grain of salt to take, you know, when you're browsing the space. Okay, anyway, back to neural networks. back to, right, more relevant neural network discussions. So part of the reason I'm coming out swinging with so many warnings, you know, because you could make the same argument for something like random forest. I know this discussion is really meta. Neural networks are shockingly easy to extend and customize, right? In fact, frameworks like TensorFlow, PyTorch, Theranos, is that what it's called? I can never remember the actual name of that. Thanos, something like that, are incredibly easy, right? They make it so easy to extend neural networks. Why, I have my conv layers here, I've got my dense layers here, and I'm just going to stack them together, and look at me, I'm making a neural network. And because neural networks are so easy currently to extend and customize, everybody does it, right? Because it seems like the right thing to do. But again, as these parameter counts increase, it becomes very difficult to understand or really interpret such that you can iterate on a neural net, what the model is actually doing. When we have, so the big ones, right, like the exceptions, the inceptions, these neural networks that, for example, teams like Google Brain have developed over years and published all these papers studying, teams of people developed those models and then developed analysis to explain why things are working or why things are doing what they're doing. So in general, my advice is that if you can use an existing architecture, if you can use even a pre-trained model to do so, simply because it feels very easy to just build your own neural network. And if your problem is simple, that makes sense, right? I wouldn't argue with you if that's what you were doing, right? But if your problem is at the level of image understanding, doing something like, oh, I've read enough about CNN, so I'm going to build my own convolutional neural net, and then I'm going to train it with all my data, and I'm just going to do what you do. My advice would be to try not to do that. And there are some ways to help when the task you're solving and the task of the existing neural network aren't exactly the same. And we'll talk about that in a second. But in general, the temptation is there, but I advise against it simply because these are very difficult to interpret functions. And in case any of you care, that's an image from the exception paper that I'm actually talking about here. Right, so that then comes the question of, if I do want to use neural networks, okay, because my problem has a very high input dimensionality, and okay, this guy's telling me not to build my own from scratch, but no neural network does what I want it to do exactly, right? Close, maybe. And that's when we get to talking about transfer learning, which in such a flexibility hasn't really been seen before neural networks, right? Our ability to domain transfer knowledge so flexibly. So in short, transfer learning is this idea of taking an existing model, and we're going to speak strictly in neural net parlance here, and adjusting the weights, not completely retraining the model, adjusting the weights to solve a different task. Okay, but that's a very intentionally ambiguous definition. Really, we're transferring knowledge that's been learned by this well-studied, perhaps trained on ImageNet or something I talked about in my some other session, I don't even remember which one at this point, JFT, right? So Google has some JFT, it's like 300 million image labeled data set that's not public, that they're training these things on, that isn't publicly accessible. We can still take advantage of all of that training and all of that knowledge without trying to have that data and train a network ourselves by using transfer learning. So this comes in a whole lot of different flavors, and because this is a neural network course, I really don't want to get into it, but I realize from the last class that it will at least be helpful to talk a little bit about transfer learning. So one really common thing to do with transfer learning when your tasks are the most dissimilar is something called refinement. And this is when I take an entire network that's been learned to do one task and train all the weights. So just train the whole network as if I was training it from scratch, but with a smaller learning rate for a smaller amount of time, so it doesn't overfit. That's refinement, and this is really ideal if your tasks from the original task the neural network is solving and yours are the most different. There's something called sub-network training, where I actually, in my, we'll say TensorFlow or something, my framework, I stop the gradient. I say, do not backpropagate the gradient any further to some piece of the network, and it's also sometimes known as freezing, and just train a subset of that network, right? So if we're talking about things going back to exception, maybe we use all of exception except the last two layers. We stop the gradient before those last two layers and just train the fully connected piece for our image labeling task. Another, possibly the simplest technique is just feature extraction, right? So sometimes published neural networks will expose intermediate tensors as outputs as features. This is a whole other thing we could get to talk about, when to do this, when not to do this. We've talked a little bit about embeddings. Sometimes these intermediate tensors happen to form good embeddings. Ask me about that later if you want to talk about how to do it. but we can cop pieces, real outputs of the existing neural network, and then combine them in a much smaller neural network to solve our task. So really, our problem then becomes using this big, chunky thing that someone has spent, decades, eons of compute time for which we've learned the weights, and then just piping those into a much simpler model because it's already extracted salient features. Yeah, and right. So transfer learning is really the technique for domain transfer of tasks of these big sort of, or pre-trained models. They don't even have to be big. And that's one of my cats. His name is Jay. So we're kind of coming to a close here. But right, so we can't talk about neural networks without a shout out to how fast they're moving, right? Or how fast the institution of neural networks is moving. Unless your job is to be a general data scientist, not even in a specific field, you should never expect to be on top of the rate at which neural networks are progressing, at the rate at which research is coming out. And if you are, you're at the wrong conference. Because I certainly am not. It's incredibly difficult to do. And this field really hasn't stabilized to a place where we can all agree upon shared solutions, except for some very basic things, right? Fully convolutional neural nets seem to be the solution to segmentation tasks. Convolutions in general are a good idea for feature extraction, but it's still difficult. I would recommend any of you who haven't to go take Google's ML crash course. Don't worry, it doesn't advertise anything to you. It is simply an introduction to machine learning using all free stuff. My analogies about manifolds and transformations and all of these other things in describing a machine learning algorithm they use the same framing, and so this should be a natural thing to go take that, and they explain things in much more detail than I can and will in the amount of time that we have. So yeah, at that, thank you so much, and I will now take questions. And we have 13 minutes left. Nobody?
I'll give it a try.
Okay.
I don't know how to explain this, but so I'm still puzzling over the don't know masking. And how is that different from, let's say, because that's assuming you know where your don't knows are, right? Whereas, let's say if you were to create an additional label to the things you're trying to predict, and say, water, forest, everything else I don't care about. How are those two things different?
Yes. So the question was, why don't I just add a class that is, I don't know what this is, right? And then have the model predict an I don't know what this is class everywhere it shouldn't know what it is, right? Everywhere we don't have annotations. And that's the first natural thing to do. However, by adding a class, right, so then the answer is that any different from don't care masking? So the problem with adding a class that is I don't know what this is now your model actually has to learn that this quantifies an I don't know what this is, and can now misidentify things, both as I don't know what this is and the other way around. And in general, you're now, right, I'm going to keep referring to this term entropic capacity, because that really refers to the learning capacity of your model. And now some of this learning capacity has to be spent learning I don't know. And because while we consider it an I don't know class, I don't know means something very specific, right? In terms of whether it's land cover or something else like that. So so the other important piece, right, of don't care masking is there's this assumption that when you're applying it in practice, that you are going to mask out or going to say I don't care about those same positions you said I don't care about when you're building the input and when you're building those masks. So I'll give you a concrete example, and hopefully this can help a little bit. So it's another Project Earth, thing related to Project Earth. So that's another thing for which we were using don't care masks, and we had cloudy data, right? We have high confidence in Landsat's QA band, cloud cover band. So part of the output of our classifier, right? So we actually ended up using an ensemble. And so we would, I think something like 10 FCNNs essentially all running in parallel, and they would produce a bunch of outputs, right? And we would take those outputs and then zero the predictions, the discrete distributions, just as we would were retraining the model with the don't care mask, right? We're repurposing these to say, I don't actually know that we predicted that distribution, but it's garbage, right? I don't actually know what that is. And then over the stack of Landsat bands, then we combine the distributions at that point. So anywhere there were zeros, that simply wasn't considered in the final combination of these outputs. So of course we have more data where it's more data where it's less cloudy in that case. But yeah, hopefully that kind of answers that question. A little bit, sort of. Yeah, again, I have office hours. I'm literally, I think, booked for 6 hours tomorrow and the day after. So I'm happy to talk about it.
Can you talk a little bit about different kinds of learning? Like in one kind of learning, you take a pixel and you produce another pixel. So you categorize it per pixel. Another kind of learning would be you take a whole region, you just want to find like a couple of points. You want to classify tailings. You want to classify this is a whatever. This is a Nile delta or something.
So, right. So the question was, can we talk a little bit about different types of image learning, image predictions, right? Today, I spoke a lot about something, if you were in the neural segmentation class, is just broadly defined as segmentation, even if it's a regression problem. But there are certainly all sorts of other insights we can pull from image data, right? Or other forms of that output, right? And one of those is like a bounding box, maybe. Or maybe it's a polygonal boundary. Maybe it's an ellipsoid, right? We want to take an image and, yeah, it's useful to classify what every pixel belongs to, but sometimes these things are right next to each other. Sometimes we want to really just draw a geometry around things in this image. Am I? That's right. All right, cool. So that's the question, right? Let's talk about that a little bit. So there's really two ways to do this. And it really depends on the data you have access to, right, and the kind of model you can train, whether or not if you happen to have bounding boxes or you don't. So I'll begin by saying there are an entire class of specifically neural network architectures that are used for bounding box extraction. These are usually some variants of something called regional CNN or RNN, RCNN. And then there's things like YOLO-net and all these stupid names. But this type of network, there's a very specific network, or really it's a pair of networks for this problem, if you're talking about neural networks. Classical image understanding algorithms like sift and different feature extraction algorithms, patch matching, also help you get bounding boxes. But when we're talking in terms of neural nets, there is this entire class where you sort of have these two stages, right? Where the first stage proposes bounding boxes and the second one classifies them as valid or not. And of course, the output is no longer just a pixel map, right? It's an actual list of bounding boxes. That being said, right, so these things exist. We did not talk a whole lot about them. You can still go sort of work with it, right? So you can still kind of go from image segmentation to bounding boxes in a specific case. And we'll talk about why you might ever make the bounding box kind of like a post-processing step. So one thing you can also do is take an image segmentation algorithm. And if you remember, one of the first constraints I said was that if things aren't too close to each other, right? Because once things start being right next to each other, then it's very hard to actually take your output and turn that into two separate objects without another whole other machine learning step. But if you're doing something like identifying dams, or identifying something like, I was talking to somebody earlier today about like cooling towers, right? We're trying to find these things which in space, right, a power plant, we don't expect these objects to be so close at low resolution imagery that they're just going to be merged into one morphological blob. We can use image morphology. So we can actually predict a segmentation, like a binary segmentation mask, and then just use something like connected components to get bounding boxes out. Of course, this only works in specific cases. And if you attended the neural segmentation class, we talked about dealing with edge artifacts by over-tiling, right? And that you can't even really reasonably make a classification of an object that's right in the corner of some sort of segmentation output. So that being said, right, we have a solution for sort of tiling segmentation over something like a sphere, right, sort of indefinitely. But what if I want to use something like RCNN? What if I want to use one of these neural networks that extract bounding boxes in a tiled, like sort of expansive tiled region? It's tricky, actually. It's pretty hard. Not like it's an unsolvable problem. It's actually very straightforward to solve, but when I say pretty hard is you have to be willing to accept certain constraints to be guaranteed it's going to work the way you intend to. So I'll also make a plug, because now I have an opportunity to make a plug. In the coming weeks, Earth Engine is adding bounding box, tiled, sort of seamless bounding box extraction from imagery. We don't have that one for AI platform, EE.model, all that stuff. So right now we just do images to images, but look in the coming weeks for also extracting bounding boxes with no edge artifacts. So yeah, and we can talk more, but it's right, another very broad field. It's because these are very drastically different output types. You first.
This might be a completely random question, but if there are certain classes that are much more easier to classify, like is it forest and water are much easier to classify, is it possible to use some sort of an exclusion principle? I say, use the classes that are easier to classify, but I'm only interested in the non-classified image. So the class that is not classified is what I'm interested in, but what I'm doing is I'm letting the model actually classify everything else so that I kind of extract out the thing that is not classified that is harder to extract.
Okay, so this almost sounds like, the question was, could we train a model to maybe this is, or hopefully this is a reduction of what you were asking, could we train a model to improve our performance on harder classes to just train a subset of the existing classes? Or could we, should we,
Yeah. Like basically if you know, there are a subset of like known classes, but what I do is like, and the model actually gives, this is like non-classified, and I'm giving you a probability that this is non-classified. The reason is the non-classified class is the harder class.
Yes, so, right. So the question being, so we were talking a little bit about sort of I don't know what this is class, right? Yeah. And could we maybe use that to help inform a follow-up process to then do a better job? And that's one way to do it. I would still recommend a different way to do this sort of procedure. Again, so what we're trying to do is build a model that's going to make some predictions, right, about something, right? We'll keep talking in terms of images so that we're sort of staying in the same lane here. And if we notice it's tending to predict things, it's having a hard time, right? The model is reporting in some way that it's having a hard time predicting these classes. Can we then use that as a useful tool to go build another classifier that's perhaps something like almost doing like a gradient boosting thing, like now predicting the error in just these classes, or just predicting these classes, or predicting these elements of the data set, and assuming we're not going to overfit because we're good scientists. Yeah, so is that a good idea? So let me also take a step back by first describing often how we output something like a categorical output, like you're talking about. So we talked about one-hot encoding, right? So that's how we sort of build features that go into the model. But when your model's making predictions, remember, it's now actually trying to output these three different, it has more outputs, right? Let's say it has like 3 outputs. So usually we talk very briefly about it. This is not a neural net specific section, but you'll often predict a probability, a discrete distribution, right? So of your 3 classes, these sum to 1, and you'll say something like, in our land cover case, we'll say it was like, I was sure this was easy, I was sure this was hard, and I was sure that this was whatever. So in fact, you're getting a confidence score, actually, when you're using one-hot encoding for categorical outputs. And instead, again, of, I'll use the phrase, encumbering the model with having to predict an entire set of other things that it might not know about, you can actually use the confidence intervals. Sometimes these are priors, these are all sorts of other things. Yeah, all sorts of the etymology is kind of all over the place, but you can use this as not just a proxy, but a sort of a straightforward, the model was this confident in this prediction. If you run into a scenario where your model was like, I was confident that this is right and this is very wrong, you're probably overfitting in that case. But my recommendation is if you wanted to do some sort of follow-up technique to say, okay, which maybe I can identify, so even if you wanted to create a map and then see which areas of the map am I least certain in my predictions, you could use the categorical confidence in this case.
So if I understand you well, you're more or less discouraging to train the complex existing models from scratch or to adapt a few layers to fit your problem. But of course, with remote sensing sensors that we use, they are 2 different from the pre-trained models. So why are you discouraging us on the one hand, and how do we cope with this problem on the other hand?
That's a great question. So the question was, I'm up here telling you, don't train a model from scratch if you don't have to. But in the remote sensing domain, we don't have anything like Inception trained on JFT, right? Like we don't have these existing models. And that's a really good point. And the truth is, yeah, I acknowledge that we don't. And that's why, unfortunately, when I say don't retrain these models, I have to say don't retrain if you don't have to. So here's, I'll give some, I have like 20 seconds left, but I'll say really briefly, if you're working with higher resolution data like red, green, blue data, actually, and something that's like, I'll give you even a number, like 15 centimeter resolution imagery, so this is like planet or flyover or something like that, you can actually, you will find success retraining something like a ResNet or an Exception or something like that. Right, if you're working with like 30 meter or 10 meter data, multispectral, it doesn't work so well. And we hear you, and we're working on it. But at this, we are out of time, so thank you so much, everyone, and I will see you guys around.